On December 19th, an interstellar object called 3I Atlas reaches a point where uncertainty becomes unavoidable. Its trajectory, brightness shifts, and timing do not fully align with standard comet models. And that gap is where serious scientific questions begin. In this episode, we focus on readiness, what astronomers, engineers, and governments examine before the event, why protocols like electromagnetic shielding are even discussed, and how incomplete data shapes public trust. We also look at the psychological impact of confirmation, not speculation, and why this moment connects to deeper questions about dark energy and Planet 9. If this kind of evidence-based exploration matters to you, like the video and subscribe. Let's begin by grounding curiosity in data. Before December 19th arrives, the timeline has already begun. Not toward impact and not toward disaster, but toward a moment that could quietly disrupt how people understand their place in space. The disruption does not come from danger. It comes from visibility. On December 19th, 3I Atlas reaches its closest approach to Earth. Officially classified as a comet, yet already challenging how comets are expected to behave. Several independent observers suggest that if its brightness continues along certain trajectories, the object may cross the threshold of naked eye visibility. That would mean a point of light from another stellar system appearing in the sky, visible without instruments, present without warning, and not following patterns familiar to most observers. Visibility matters because it changes scale. Something seen only through telescopes remains distant in the public mind. Something visible to the unaided eye becomes immediate. It becomes shared. Millions of people could look up within the same night and see a light that does not belong to any known planet, satellite, or constellation. It would not announce itself as extraordinary, yet it would refuse to fit into learned categories. That moment alone would raise questions that have little to do with danger and everything to do with understanding. 3I Atlas is projected to pass at a distance of roughly 1.8 astronomical units from Earth, or about 270 million kilometers. That distance sounds vast, and in physical terms, it is. But astronomical visibility is not controlled by distance alone. It is controlled by brightness. And brightness depends on composition, surface activity, and how material responds to solar heating. In that sense, interstellar objects are among the least predictable visitors. They formed around other stars, under conditions we do not fully know, carrying histories written far outside the environment that shaped objects native to our solar system. Current mainstream models place 3I Atlas at a visual magnitude between 11 and 12 at closest approach. That range keeps it firmly within telescope-only visibility. Human vision under dark skies typically reaches down to about magnitude 6. Under those assumptions, there would be no reason to expect widespread visibility. However, the confidence behind those numbers is not absolute. Observations made by independent astronomers and amateur networks suggest episodes of unexplained brightening. These events appear as brief flares or pulses in the light curve, moments when the object becomes brighter than expected before fading again. The interest in these reports does not come from speculation alone. It comes from how comets behave when they contain volatile materials that respond sharply to heat. When the James Webb Space Telescope examined 3I Atlas in the infrared, it revealed a coma dominated by carbon dioxide rather than water. The coma is the cloud of gas and dust that surrounds a comet's solid core. In most solar system comets, water ice is the primary driver of activity as the object warms. Here, carbon dioxide appears to play the dominant role, with smaller contributions from water, carbon monoxide, dust, and other frozen compounds. This chemical profile matters because carbon dioxide sublimates at lower temperatures than water ice. Sublimation is the process by which a solid turns directly into gas without passing through a liquid phase. As 3I Atlas moves closer to the Sun, carbon dioxide trapped beneath the surface can transition rapidly into gas, building pressure and escaping suddenly. These releases can produce sharp increases in brightness over short periods of time. They can also occur unevenly, depending on how volatiles are distributed within the nucleus. The composition suggests that 3I Atlas formed in a colder region around another star, likely far from its original sun, where volatile compounds remained stable for long periods. In such environments, material can accumulate in layers that respond unpredictably when exposed to stronger sunlight. Once inside our solar system, those layers encounter thermal conditions they were never shaped to handle. That mismatch is one reason astronomers approach brightness predictions for interstellar comets with caution. If an unexpected brightening were to occur near December 19th, the consequences would extend beyond astronomy. A visible interstellar object would generate immediate public attention. It would invite interpretation, speculation, and pressure on institutions to explain what is being observed. The act of seeing, simple and direct, carries psychological weight. It turns abstract knowledge into direct experience. Humanity has long known that material moves between star systems, but rarely has there been an opportunity for that fact to be felt rather than understood. Scientific institutions emphasize that 3I Atlas shows no confirmed signs of artificial behavior. Its trajectory follows gravitational expectations. Its activity can be explained within known physical processes. These statements are grounded in evidence and probability. At the same time, science operates within confidence intervals, not absolutes. Only a handful of interstellar objects have ever been detected, and none have been observed through a complete solar encounter with today's instruments. The sample size is small enough that uncertainty remains an inherent part of every conclusion. This uncertainty becomes most visible in the debate over the object's light curve. A light curve is a record of how an object's brightness changes over time. For comets, light curves can reveal rotation, surface activity, and internal structure. Measuring them sounds straightforward, but in practice, it is influenced by atmospheric conditions, instrument sensitivity, viewing angle, and background light. Small differences in measurement technique can produce noticeably different results. Amateur astronomers using backyard telescopes and digital sensors have reported irregular bursts of brightness. These variations appear over timescales of hours to days. Some observers believe they see rough cycles, suggesting that active regions on a rotating nucleus may be sweeping into view. Others suggest internal stress, cracking, or sudden releases of gas from beneath the surface. These interpretations remain tentative, shaped by data collected near the limits of detection. Institutional observatories report more conservative findings. Large ground-based telescopes and space-based platforms show an object whose brightness changes can be accounted for by standard cometary behavior. From this perspective, variations fall within expected ranges driven by solar heating and gas release. The difference between these datasets does not necessarily imply error. It reflects the fact that different instruments measure different aspects of the same phenomenon, often at different times and resolutions. Some independent observers have proposed a repeating cycle in the brightness, ranging from roughly 11 to 16 hours. They argue that the pattern is too structured to be random and too irregular to be explained by simple rotation alone. Online communities have assembled extensive data sets, comparing measurements and searching for consistency. These efforts highlight both the strength and the limitation of distributed observation. They expand coverage but also amplify uncertainty when signals approach the noise floor. None of these claims have been confirmed through peer-reviewed analysis. That absence of confirmation is not evidence of concealment. But it does underscore how early the process remains. Interstellar objects challenge assumptions built from centuries of studying bodies formed under similar conditions. When those assumptions are applied beyond their tested range, disagreements naturally arise. The broader implications are not about proving something extraordinary. They are about recognizing how limited current frameworks can be when confronted with rare events. Even without any risk to Earth, a visible interstellar visitor would prompt deeper conversations about how often such objects pass through our system, what they carry, and how little we may notice under ordinary circumstances. It would challenge the idea that space around Earth is quiet and uneventful. December 19th remains on the calendar, an ordinary date. Yet it also represents a point where observation, uncertainty, and public awareness could intersect. If many people look up and see something unfamiliar, the sky may feel different, not because it has changed, but because attention has. Every photon reaching human eyes carries information from vast distances. In this case, that information would come from another star system, arriving without intent, without message, and without concern for whether humanity feels prepared to receive it. As attention turns toward the data itself, disagreements over brightness measurements and light curves come into sharper focus. Numbers are expected to be objective. Data is expected to clarify. Yet when tracking an interstellar object moving rapidly through the inner solar system, clarity is often the first thing lost. Small differences in methodology, timing, and instrumentation can compound into competing interpretations. And those interpretations begin to shape expectations for what the coming weeks may reveal. It is within this narrowing gap between measurement and meaning that consensus has proven difficult to reach. The conflict over data matters precisely because data never exists in isolation. Measurements do not simply describe reality, they frame interpretation, guide expectation, and ultimately shape the public narrative around what is being observed. If institutional measurements are taken as the primary reference, then 3I Atlas appears to be a comet behaving largely as expected. Its interstellar origin makes it scientifically valuable. But its activity, brightness, and motion remain within familiar bounds. In that framing, there is nothing urgent to resolve beyond refining models and accumulating additional observations. The object becomes another data point, unusual in origin but ordinary in behavior. If, however, greater weight is given to independent observations, the picture changes. The object begins to look more complex. Brightness variations appear structured rather than random. Patterns suggest internal processes that are not yet fully described by existing comet models. These interpretations do not require extraordinary explanations. But they do imply that 3I Atlas may be revealing physical behaviors not previously observed in detail. In an environment where information spreads instantly, both narratives circulate at the same time. The result is not clarity, but overlap, contradiction, and confusion. One explanation for why agencies emphasize conservative interpretations is simple caution. Scientific institutions are structured to avoid premature conclusions. Claims must survive verification, replication, and review before they are endorsed. An unusual brightness report that later turns out to be instrumental noise or atmospheric interference would undermine trust. In that context, restraint is not concealment, it is a standard response to uncertainty. There is also an institutional reality that shapes communication. Space agencies operate within political and financial systems. They manage multiple missions, long timelines, and limited resources. Public attention driven by sensational claims can disrupt planning and distort priorities. If 3I Atlas ultimately proves unremarkable, early emphasis on anomalies would appear irresponsible. From that perspective, it is safer to understate until certainty increases. At the same time, caution does not eliminate the possibility that some independent observers are detecting real phenomena. Carbon dioxide-driven outgassing can produce sudden jets as subsurface pockets heat and rupture. These events can cause sharp increases in brightness without lasting change. If the nucleus is irregular in shape and rotation, active regions may face Earth on repeating schedules, creating apparent periodicity. All of these explanations fall well within natural physics. They would deepen understanding of interstellar objects without challenging foundational assumptions. There is, however, another category of interpretation that occupies a more uncomfortable space. It does not dominate mainstream discussion, but it persists at the margins. This view suggests that some brightness changes may reflect more than random release of gas. Cracking of ancient irradiated surfaces could expose fresh material in organized ways. Venting could follow internal pathways shaped over long timescales. These ideas still rely on natural processes, but they imply structure that is not yet fully characterized. More speculative interpretations go further. They propose that brightness variations could reflect changes in orientation or energy state that are not easily explained by standard models. These ideas are not supported by evidence, and they are not endorsed here. They persist because the observational context is unusual. This is an interstellar object, observed with limited precedent, carrying properties shaped far beyond the environment where current models were developed. In that gap between knowledge and observation, speculation naturally arises. The disagreement over data will not resolve itself before December 19th. Closest approach will occur while competing interpretations remain active. Professional and amateur observers will be watching the same sky, collecting different kinds of data, and reaching different conclusions. That unresolved ambiguity may be more unsettling than any confirmed anomaly, because it resists closure. Attention then turns to the object's motion. Objects in space follow predictable rules. Gravity governs trajectories, linking position, velocity, and time through relationships tested over centuries. These principles allow precise navigation across the solar system. When an interstellar object enters this environment, its path should be calculable with similar confidence. 3I Atlas follows a hyperbolic trajectory. Unlike bound objects that return periodically, it enters once and leaves, carrying excess velocity beyond what the Sun can capture. This confirms its interstellar origin. It came from elsewhere and will return to the space between stars. That fact is not disputed. The debate centers on the fine details of how it moves while passing through. Comets experience non-gravitational acceleration. As they warm, volatile materials sublimate and escape as gas. These jets create small thrust forces, altering motion slightly. Astronomers account for this by adjusting trajectory models. For 3I Atlas, this process should be manageable. The presence of a carbon dioxide-dominated coma confirms active outgassing. Estimates place the nucleus size somewhere between 440 meters and 5.6 kilometers in diameter. This wide range reflects uncertainty in reflectivity and activity. Using these estimates, scientists calculate expected thrust from observed outgassing and compare it to measured motion. Most analyses find agreement within acceptable margins. The object behaves as expected for a comet of its estimated size and composition. A smaller group of analysts, including some with experience in orbital dynamics, argue that subtle discrepancies remain. After accounting for expected outgassing, they report residual deviations that persist. These deviations are small, but measurable. They suggest that observed acceleration may be slightly higher than predicted. From this emerges a controversial figure, approximately 0.3%. This is not a probability that the object is artificial. It is not evidence of engineering. It represents a statistical mismatch between models and observations. In most contexts, such a number would be dismissed as noise, uncertainty, or incomplete modeling. This context is different. Only a few interstellar objects have been observed in detail. The first, Oumuamua, displayed unexplained acceleration without a detectable coma. That anomaly generated years of debate and multiple natural explanations, including invisible hydrogen outgassing and radiation pressure effects. While most researchers accepted these explanations, discussion persisted. 3I Atlas shows similar issues at a much smaller scale. The unexplained component is tiny, well within uncertainty, yet its presence invites comparison. It suggests that interstellar objects may not behave exactly like those formed in our solar system. Long exposure to cosmic radiation, extreme temperature cycling, and deep space chemistry may alter internal structure in ways not yet captured by existing models. There is also a more speculative interpretation that remains firmly unproven. It suggests that subtle trajectory adjustments could reflect controlled processes rather than random outgassing. Stabilization effects, asymmetric venting, or mass distribution could, in theory, influence motion. These ideas remain hypothetical. They are noted not because they are likely, but because mathematics does not entirely forbid them. A non-zero probability matters not because it proves anything, but because it allows possibility. In a world shaped by uncertainty, even small probabilities can carry psychological weight. They transform an object from familiar to ambiguous. They invite attention beyond scientific interest. As additional observations refine trajectory models, that probability will change. It may shrink to zero. It may disappear into measurement noise, or it may persist long enough to demand better explanation. Regardless of outcome, this episode reinforces a broader lesson. Interstellar space is active. Objects pass between stars more often than once believed. Each one carries data shaped by environments far beyond Earth's experience. It also raises a final, quieter question. Scientific observation is not the only way objects are watched. Some forms of attention are passive, classified, and deliberately unobtrusive. If 3I Atlas is being monitored through other systems, with other priorities, that attention would leave little public trace. Understanding why requires looking beyond astronomy itself and examining how different institutions observe the unknown. Science, at least in its public form, is built on openness. Observatories publish raw measurements. Research groups release calibrated data. Findings move through peer review and appear in journals, where results can be questioned, replicated, or refined. This process forms the backbone of modern astronomy. It ensures discoveries become shared knowledge rather than private insight. Yet this public-facing system represents only one layer of observation. Another layer exists beyond it, rarely visible in astronomical bulletins or agency announcements, where instruments designed for entirely different purposes can be quietly redirected when something unfamiliar enters the sky. Fragmented reports and carefully worded comments from officials suggest that 3I Atlas has attracted attention from organizations that do not normally focus on comets. This attention does not show up as press releases or conference briefings. Instead, it follows a quieter pattern that has existed for decades. When an object introduces uncertainty, especially uncertainty that intersects with public speculation, observation expands beyond academic science. It enters a domain shaped by risk assessment and contingency planning. To describe this, it is useful to introduce the idea of a passive observation protocol. This is not an official name, but a functional description. Passive observation means no active signaling toward the object, no radar illumination, no laser ranging, no attempts to probe or interact. The goal is not engagement. The goal is reception. Instruments remain silent while they collect. Every photon is logged. Every radio fluctuation is recorded. Every charged particle detected as the object moves through the solar environment becomes part of a growing archive. The word protocol implies preparation rather than reaction. It suggests that there are established procedures for situations that fall outside routine expectations. These procedures are not dramatic plans pulled from a shelf. They are distributed practices embedded across agencies and networks. Historically, the labels attached to such protocols tend to come from contingency planning language, often reserved for scenarios that are considered unlikely but consequential, the kind of scenarios that seem excessive until circumstances change. Public records already show that 3I Atlas is receiving attention beyond what its zero-impact probability would normally require. The International Asteroid Warning Network, which typically focuses on objects that pose a collision risk, has allocated resources to tracking this visitor. Solar physics spacecraft operated by space agencies have also been observing it, even though they were designed primarily to study the sun and the solar wind. For many of these instruments, this marks the first time they have been used to monitor an interstellar object. The result is an unusual data set. Measurements intended to understand solar plasma and magnetic fields are now intersecting with observations of a visitor from another star system. This blending of disciplines was not part of the original mission plans. It reflects adaptive use of existing infrastructure rather than a targeted response. The coverage is sustained, global, and coordinated enough to suggest that interest extends beyond individual research teams. At this point, confirmed fact begins to give way to informed speculation. Deep space monitoring systems often serve dual purposes. Radio telescopes that search for natural astrophysical signals can also detect structured emissions. Very low-frequency arrays designed to study Earth's magnetosphere and ionosphere can register electromagnetic disturbances originating far beyond the planet. These systems are sensitive to interactions between charged particles, magnetic fields, and moving bodies in space. None of these instruments were built with 3I Atlas in mind, yet they can be repurposed quickly when something unusual appears. The data they collect does not always flow into public databases. Some streams are filtered. Some are archived. Some remain accessible only within operational contexts. This does not imply concealment. It reflects the reality that not all data pipelines are designed for open publication. It is important to state clearly what is being claimed and what is not. There is no evidence that intelligence agencies have detected artificial transmissions from 3I Atlas. There is no verified data indicating that the object is engineered or controlled. The claim is narrower and more grounded. When an interstellar object generates uncertainty, public attention, and competing interpretations, it naturally falls within the scope of organizations tasked with monitoring unknowns that could affect infrastructure, security, or public stability. An object from another star system passing through the inner solar system qualifies as such an unknown. Even with zero impact risk, its unfamiliar origin and behavior justify monitoring. Failing to observe would be more unusual than observing. This perspective helps explain why attention might extend beyond astronomers. Online communities have responded to this gap by conducting their own monitoring. Amateur observers, particularly those interested in fringe science and electromagnetic phenomena, have reported unusual very low-frequency noise detected by hobbyist stations. Some claim these signals align in time with reported brightness variations of 3I Atlas. These reports are anecdotal. They lack calibration standards. They have not been confirmed by professional instruments. They could easily result from terrestrial interference, atmospheric conditions, or instrument drift. Still, they persist across multiple locations. That persistence does not validate the signals, but it does indicate coordinated attention. People are sharing timestamps, comparing data, and attempting to identify correlations that would not be visible to isolated observers. History provides context for how this relationship between security infrastructure and cosmic observation has evolved. During the Cold War, satellites designed to detect nuclear detonations recorded meteor explosions. That data, once declassified, contributed significantly to understanding asteroid impacts. In later decades, classified sensors detected meteors that went unnoticed by public networks. With data released years later after sensitivities expired, the boundary between strategic monitoring and scientific discovery has always been porous. Dual-use technologies routinely generate insights that extend beyond their original purpose. If similar infrastructure is observing 3I Atlas now, public acknowledgement may never occur, or it may arrive long after interest has faded. Several reasons explain why observation might remain quiet. Premature disclosure risks misinterpretation. Anomalous signals require careful verification before entering a media environment that rewards speed over accuracy. There is also the question of observational advantage. If unexpected behavior were detected, gathering data without drawing attention would be prudent. International considerations matter as well. Space is increasingly contested. Discoveries tied to interstellar objects could influence discussions around planetary defense, space security, and governance. Managing information becomes part of managing relationships between nations. Another interpretation reframes the situation entirely. Passive observation may be less about 3I Atlas itself and more about the response to it. The object becomes a rehearsal, a chance to test detection systems, data integration workflows, and interagency coordination. In this view, the value lies not in what the object is, but in how institutions respond under uncertainty. As December 19th approaches, observation intensifies, somewhere in facilities that do not appear in public directories. Analysts are watching data streams that will never appear in journals. They are running models that will not be peer-reviewed. They are asking questions that sound unreasonable in public discourse, but are routine in risk assessment. Time compresses as the date approaches. Months of observation narrow into a critical 72-hour window before closest approach. This is when uncertainty peaks. It is when abstract contingency planning becomes operational. Final data consolidation occurs as observations from observatories, spacecraft, and monitoring networks are merged into a single working picture. Modeling teams explore not only the most likely outcomes, but also the low-probability tails of the distribution. Communication strategies are refined. Decisions are made about what to release publicly, how to frame uncertainty, and how to avoid either panic or dismissal. operational readiness follows. Communications infrastructure receives heightened scrutiny. Satellite systems that support navigation, timing, finance, and global connectivity are evaluated for resilience. Backup systems are placed on standby. These measures are not driven by expectation of failure, but by the recognition that redundancy is cheaper than recovery. Emergency services may also be briefed, not for impact scenarios, but for social response. If 3I Atlas were to brighten unexpectedly and become visible without instruments, public reaction could shift quickly. Increased call volumes, distracted driving, and stress responses are realistic outcomes. These are not dramatic scenarios. They are mundane consequences of uncertainty intersecting with attention. These preparations do not imply danger. They reflect how institutions manage low probability, high consequence situations. Whether they prove necessary or excessive will only be clear in hindsight. What is certain is that observation is occurring on multiple levels. The sky is being watched more closely than most people realize. And not all of those observers are astronomers. One of the most visible examples of this broader observational landscape lies in the systems designed to detect meteors and small bodies. These networks were built for a specific purpose: early warning. They exist to identify objects that could threaten Earth and to track their motion with enough precision to support decision-making. During the period surrounding the passage of 3I Atlas, these systems may shift into an elevated alert posture. This shift does not reflect impact risk. It reflects opportunity. An interstellar object provides a real-world test of detection, tracking, and coordination capabilities that are otherwise exercised only through simulations. From a planetary defense perspective, this matters. Simulations are useful, but they do not fully replicate the complexity of real data. An actual interstellar visitor tests sensor sensitivity, data integration, and international cooperation under live conditions. It reveals how quickly information moves between institutions, how well models converge, and where friction appears in decision-making processes. 3I Atlas allows these systems to be exercised without the pressure of imminent danger, which is the ideal environment for identifying weaknesses before they matter. Preparation is not only technical, it is psychological. Organizations responsible for managing uncertain risks operate within a narrow band between readiness and overreaction. Too little preparation leaves them exposed if something unexpected occurs. Too much preparation signals alarm and can amplify fear, creating the very disruption they are trying to avoid. Effective readiness is calibrated. It is proportional to probability, weighted by consequence. In the case of 3I Atlas, the probability of truly anomalous behavior is low. That assessment is supported by current data and physical models. At the same time, the consequences of being unprepared, should anomalies occur, are significant enough to justify more than casual attention. Preparation, in this context, is not about expecting the worst. It is about acknowledging uncertainty. What kinds of anomalies are considered in such planning? One scenario involves a sudden brightness increase. If the object were to brighten unexpectedly and become visible to the unaided eye, millions of people could see it simultaneously. That moment would create immediate global awareness of something unfamiliar in the sky, even without danger. Such an event would demand explanation and coordination. Another scenario involves unexpected changes in trajectory, not changes that imply impact risk, but deviations that challenge assumptions about purely natural behavior. There is also the possibility of detecting structured emissions, radio signals, or optical patterns that do not align with random thermal processes or simple reflection. Fragmentation events are also considered. A nucleus breaking apart could reveal interior structure or create multiple objects where there was previously one. Any of these developments would alter both scientific and public perception. An object that had been framed as interesting but non-threatening would become a phenomenon requiring rapid interpretation. The challenge then becomes communication. Public messaging around preparation is inherently delicate. Advising readiness without context creates anxiety. Explaining low-probability scenarios in detail can give them disproportionate weight. Most agencies attempt to strike a balance. They emphasize what is known, acknowledge uncertainty without dramatizing it, and clearly state the absence of danger. The tone matters. Excessive reassurance can feel dismissive. Excessive caution can feel alarming. Whether this balance holds during the final 72 hours before closest approach depends on how data evolves and whether uncertainties narrow or widen. For individuals wondering whether they should take specific actions as December 19th approaches, the objective answer is straightforward. There is no credible threat that requires personal emergency preparation. Normal awareness is sufficient, subjectively. However, people respond to uncertainty differently. Some find reassurance in simple actions that increase a sense of readiness. These actions are not extreme. Checking communication plans with family and friends, ensuring access to important information offline, following reliable sources rather than rumor-driven speculation. These steps are broadly applicable to any situation where attention may shift suddenly or information flow may become uneven. If nothing unusual happens, they cost little. If something does occur, they may help maintain stability. If December 19th passes quietly, with nothing more than additional scientific papers and updated models, then preparation will appear unnecessary in hindsight. But if the 72-hour window reveals something unanticipated, small steps taken in advance may prove useful. This logic underlies institutional readiness as well as personal choices. Attention then turns to a different category of concern. Not impact, not trajectory, but electromagnetism. Modern civilization depends on electricity and electromagnetic communication in ways that are easy to overlook. Every device, every network, every timing system relies on controlled flows of electrons and electromagnetic fields carrying information at the speed of light. This infrastructure was built under assumptions of relative electromagnetic stability. Solar storms are the primary known exception. They are monitored, modeled, and mitigated. An interstellar object passing through the solar environment introduces a different variable. Not because it is expected to cause disruption, but because its properties are less well understood. 3I Atlas has a coma dominated by carbon dioxide. This coma extends thousands of kilometers into space. Solar ultraviolet radiation ionizes this gas, creating plasma. Plasma consists of charged particles that respond to electromagnetic fields, the solar wind. A constant flow of charged particles from the sun interacts with this plasma, draping magnetic field lines around the coma and creating a dynamic electromagnetic structure. All of this is expected behavior. It has been observed in many solar system comets. What distinguishes 3I Atlas is its history. Research suggests that long exposure to galactic cosmic rays over millions or billions of years may have transformed its surface. Cosmic rays are high-energy particles capable of breaking chemical bonds and forming complex compounds over long timescales. This process can produce an irradiated D6-nide, organic rich crust unlike anything seen in comets native to our solar system. When this crust is heated and disrupted by outgassing jets, fresh material is exposed. The electromagnetic properties of such material may differ from expectations based on familiar analogs. Rapid sublimation does more than release gas. It moves ionized material through magnetic fields, potentially generating brief, localized electromagnetic disturbances. It is important to place scale in context. An electromagnetic pulse, as commonly understood, involves energy levels far beyond what a comet can produce. Nuclear detonations and major solar eruptions operate on entirely different orders of magnitude. 3I Atlas is not capable of generating global electromagnetic effects. At a distance of roughly 1.8 astronomical units, any electromagnetic disturbances associated with the comet would dissipate long before reaching Earth. They could, in principle, affect instruments or spacecraft operating very close to the object. No such missions are planned during this passage. So why consider this at all? Because it highlights gaps in direct measurement. We do not have in situ data on the electromagnetic environment of an interstellar comet. We infer behavior from models built on solar system examples. Those models may be accurate. They may also be incomplete. Faraday Defense becomes relevant in this context, not as a reaction to 3I Atlas, but as a general principle. A Faraday cage is a conductive enclosure that blocks external electromagnetic fields. When electromagnetic waves strike the enclosure, they induce currents that generate opposing fields, canceling the disturbance inside. At a household level, Faraday Defense is simple. Unplugging devices reduces vulnerability. Surge protectors limit damage from voltage spikes. Storing critical electronics in conductive containers provides additional shielding. Keeping offline copies of important data reduces dependence on continuous connectivity. These practices are not specific to comets. They apply to solar storms, grid failures, and routine electrical disturbances. At a societal level, electromagnetic hardening of infrastructure is an ongoing engineering concern. Power grids, communication networks, and financial systems incorporate redundancy and protective design to prevent cascading failures. The historical example most often cited is the Carrington event of 1859, a solar storm that induced currents strong enough to disrupt telegraph systems. It serves as a reminder that Earth's electromagnetic environment can occasionally challenge technology. 3I Atlas cannot produce anything comparable. The energy scales differ by orders of magnitude. Still, considering electromagnetic readiness is part of broader resilience planning. It reflects an understanding that space is not empty or inert. It is an active environment that occasionally intersects with human systems in unexpected ways. The most likely outcome remains unchanged. 3I Atlas will pass. Instruments will measure its plasma interactions. Models will be refined. Knowledge will increase. No disruption will occur. But low probability events do occur. And when they do, the difference between inconvenience and crisis often lies in whether preparation existed at all. In this context, Faraday Defense is not about fear. It is about acknowledging that technology operates within a physical environment humanity does not fully control, and that rare events sometimes expose assumptions we did not realize we were making. Once the discussion moves beyond infrastructure and electromagnetic resilience, another question naturally follows, not one about machines, but about matter itself, and whether objects from beyond our solar system carry implications that extend into biology. The biological question surrounding 3I Atlas is one that most scientists approach with caution, not because it lacks scientific grounding, but because it sits at the intersection of chemistry, uncertainty, and public imagination. Life on Earth did not appear suddenly. It emerged from chemistry, simple molecules such as amino acids, nucleotides, and lipids accumulated through natural processes operating over immense spans of time. These molecules interacted, combined, and eventually formed systems capable of replication and evolution. None of this required intention. It required time, energy, and the right conditions. Those molecular building blocks did not come from nowhere. They formed in environments rich in carbon, hydrogen, oxygen, and nitrogen. They assembled through chemical pathways that can operate wherever similar conditions exist. This leads to a question that challenges a deeply rooted assumption. Are those ingredients unique to Earth? Or are they common throughout the universe? And if they are common, how do they move from one place to another? Objects like 3I Atlas provide a possible mechanism. An interstellar body is not bound to a single planetary system. It forms around one star, is ejected through gravitational interactions, and then spends millions or billions of years traveling through interstellar space. During that journey, it carries its chemistry with it. When such an object passes through another system, it delivers material shaped far beyond the local environment. The known composition of 3I Atlas already makes it an important scientific target. Observations from the James Webb Space Telescope have detected carbon dioxide, water, carbon monoxide, dust, and complex ices in its coma. Additional studies suggest that long exposure to galactic cosmic rays has altered the surface of the nucleus. Cosmic rays are high-energy particles that penetrate matter and drive chemical change by breaking molecular bonds and forming new compounds. Over long periods, this process can create an outer layer rich in complex organic molecules. Organic molecules are not life, they are carbon-based compounds. And carbon chemistry is widespread in the universe. Organic molecules form in molecular clouds, in protoplanetary disks, and on the surfaces of icy bodies exposed to radiation. Their significance lies in what they enable. They are the raw materials from which biology can emerge if conditions allow. This distinction is essential. Detecting organic chemistry does not mean detecting life. It means detecting potential. Panspermia is the hypothesis that life, or at least the ingredients for life, can be transported between planets or star systems by comets, asteroids, and interstellar debris. The idea has been discussed in scientific literature for more than a century. Some researchers consider it a plausible mechanism for distributing prebiotic chemistry across the galaxy. Others point to the extreme challenges involved. The primary challenge is survival. Interstellar space is harsh. High-energy cosmic radiation permeates the galaxy and steadily degrades complex molecules. Any exposed biological organism would be destroyed over long timescales. The vacuum of space removes volatile compounds. Temperature cycling between near absolute zero and periods of solar heating places additional stress on molecular structures. Because of these conditions, the mainstream scientific view is conservative. If 3I Atlas ever contained biological material when it formed, that material would almost certainly be non-viable today. Radiation would have sterilized it. Chemical processes would have altered it. Impacts with interstellar dust would have fragmented it. The organic molecules detected are best explained as products of radiation chemistry rather than remnants of life. Still, uncertainty remains at the margins. Radiation penetration is limited. Estimates suggest that cosmic rays penetrate meters, perhaps tens of meters, depending on material density and composition. A nucleus several kilometers in diameter could shield its deep interior. Material sealed within such a core might remain relatively protected over geological timescales. If that interior contains complex organic chemistry formed under different stellar conditions, then 3I Atlas represents something rare. it becomes a natural sample from another planetary system. Not evidence of biology, but evidence of chemistry shaped elsewhere. Spectroscopy could, in principle, detect unusual organic signatures, isotopic ratios that differ from solar system norms, molecular complexity that reflects unfamiliar reaction pathways. So far, no such signatures have been confirmed. Published data describe a comet whose composition is unusual mainly for its high carbon dioxide content. Spectroscopy has limitations. It detects abundant materials interacting with light at accessible wavelengths, rare compounds, buried materials, or chemistry that does not produce strong spectral features can remain invisible. The idea that interstellar organic material poses biological risk remains unsupported. Earth has been bombarded by comets and asteroids for more than 4 billion years. Many of those objects originated in distant regions of the solar system, and some may have been captured interstellar bodies early in the Sun's history. If extraterrestrial chemistry were inherently dangerous, Earth's biosphere would reflect that legacy. Meteorite studies provide clear precedent. Carbonaceous meteorites contain amino acids and other complex organic molecules. These discoveries reshaped understanding of prebiotic chemistry. They showed that life's ingredients are widespread. They did not introduce biological threats. The molecules were inert chemicals, not organisms, not self-replicating systems. 3I Atlas almost certainly belongs in this category. Even if it carries highly unusual organic chemistry, it would be scientifically valuable, not biologically hazardous. The persistence of speculation reflects something deeper than risk. It reflects a question about connection. Is Earth an isolated biological experiment, or part of a larger system where chemistry moves between stars? If interstellar objects routinely carry organic material, then planetary systems are not closed environments. Material escapes, travels, and occasionally arrives elsewhere. The galaxy becomes a network of exchange rather than a collection of isolated systems. Consider a hypothetical scenario. If a probe could land on 3I Atlas, drill into its interior, and retrieve pristine material, what would it reveal? Familiar ices in expected ratios, or chemistry that does not match anything observed in the solar system? Molecular structures shaped by processes we do not yet understand. That question cannot be answered with this object. It is moving too fast. It was detected too late. By the time a mission could reach it, it will be leaving the solar system. But the question will return with every future interstellar visitor, and the fact that scientists are willing to ask it marks a shift. The cosmos is no longer viewed only as a realm of physics and motion. It is also a context for chemistry that can, under the right conditions, give rise to biology. This leads to a different kind of consequence. Not biological danger, but psychological impact. Human societies operate on shared assumptions. The sun rises. Gravity pulls downward. Earth is our home. The universe follows understandable rules. These assumptions form a stable framework for daily life. When one of these assumptions is challenged, disruption follows. Psychologists describe this as paradigm shock at a civilizational scale. The effect spreads through what can be called the psychosphere, the shared mental environment of humanity. History offers examples. The first nuclear test in 1945 did not only demonstrate a weapon, it forced humanity to confront the reality of self-annihilation. The first human landing on the moon in 1969 did not only mark technological achievement, it transformed perspective, showing Earth as a small, fragile sphere in darkness. These events reshaped politics, culture, and philosophy. They required collective narratives to adjust. If observations of 3I Atlas were to reveal behavior incompatible with natural comet models, even without confirming artificial origin, a similar adjustment would begin. Information would spread rapidly. Official statements would compete with informal channels. Billions of people would encounter uncertainty at the same time. Reactions would vary. Some would respond with curiosity and wonder, others with anxiety and fear. Religious frameworks would reinterpret. Conspiracy narratives would claim validation. Financial markets would react to ambiguity, because uncertainty is difficult to price. This is not a prediction of chaos. It is a model based on past responses to paradigm-shifting information. The object itself would not need to be extraordinary. The impact would come from what it implies. At present, nothing indicates that such a shock is imminent, but the possibility exists because uncertainty exists. And it is uncertainty, more than danger, that shapes attention and preparation as 3I Atlas continues its passage through the solar system. One of the earliest measurable effects of a large-scale psychosphere shock would likely appear in economic systems. Financial markets are highly sensitive to uncertainty, especially uncertainty that cannot be easily quantified. If credible information suggested that 3I Atlas was more than a natural comet, even without clear danger, temporary drops in stock markets would not be surprising. Currency exchanges could become volatile as investors seek stability. Certain goods might see short-term demand spikes as people engage in precautionary behavior without being able to fully articulate what they are preparing for. This disruption would not necessarily be catastrophic. It would be uneven and temporary, but it would be measurable. Another data point in how human systems respond when confronted with cosmic unknowns rather than conventional threats. The behavior would mirror responses seen in other uncertain events, but with a different trigger. Not disease, not violence, but information that challenges deeply held assumptions about humanity's place in the universe. Social trust in institutions would face a more serious test. If revelations came after weeks or months of official reassurance that 3I Atlas was simply a comet, people would begin to question what else might have been understated or delayed. Even if earlier statements were made in good faith based on available data, the perception of reversal matters. Trust is shaped not only by accuracy, but by consistency. If information instead emerged through leaks or unofficial channels before confirmation by authorities, suspicion would grow in a different direction. People would ask why confirmation took so long and whether information had been withheld intentionally. In either case, the gap between what the public knows and what it believes institutions know becomes fertile ground for alternative narratives. In such environments, conspiracy theories thrive. They offer simple explanations for complex situations. They assign intent where uncertainty exists. They provide emotional clarity when official explanations emphasize nuance and probability. These narratives often spread faster and feel more compelling than measured scientific statements, especially when amplified by modern communication networks. Information cascades would intensify the effect. In connected societies, beliefs and behaviors propagate through social networks. Seeing others react in a certain way increases the likelihood of adopting similar responses. If enough people begin preparing for disruption, that preparation itself can produce disruption. If enough people question official explanations, skepticism becomes a social fact, regardless of whether it is justified. Social media algorithms would play a significant role. Systems designed to maximize engagement tend to promote emotionally charged content, posts that provoke fear, outrage, or awe spread more rapidly than careful analysis. Minority views that generate strong reactions can gain disproportionate visibility, while balanced assessments struggle to compete for attention. Historical parallels offer some guidance, but limited reassurance. Pandemics have demonstrated how societies oscillate between cooperation and hoarding, trust and suspicion, adaptation and breakdown. Wars and terrorist attacks show how quickly normal routines can shift when threats feel immediate. But 3I Atlas would represent a different category of shock, not a direct threat, but a revelation about context, about humanity's relationship with the cosmos. The closest parallel may be the gradual realization during the 20th century that Earth is not central, that it is one planet around an ordinary star in a galaxy containing hundreds of billions of stars. That shift reshaped philosophy and science. But it unfolded over decades. It was absorbed slowly. A sudden confirmation that an interstellar object might be artificial would compress that adjustment into days or weeks. Institutional response strategies in such a scenario would involve difficult trade-offs, a controlled release of information, gradually sharing data as understanding improves. Can minimize immediate panic, but it carries the risk of later accusations of concealment when the full picture emerges. Full transparency. Releasing all available data immediately, including uncertainties and conflicting interpretations. Preserves openness, but can overwhelm people who lack the context to evaluate ambiguous information. Neither approach is without cost. The choice made in the first hours and days following a revelation would shape public response long afterward. Trust, once damaged, is difficult to restore. Fear, once triggered, is difficult to contain. It is important to emphasize that this discussion describes a hypothetical scenario, a thought experiment. The most likely outcome remains that 3I Atlas is a natural comet, that it passes without incident, and that the primary surprise is how much speculation surrounded something ordinary. But thinking through civilizational response to paradigm-shifting information is not wasted effort. Future interstellar visitors will arrive, at some point, perhaps decades or centuries from now. Humanity may encounter evidence that forces a reassessment of long-held assumptions. How society responds will depend partly on whether such possibilities have been considered in advance. If a psychosphere shock were to occur, if December 19th marked a clear before and after in collective consciousness, the central question would not be what the object is, but how resilient human systems are, whether social structures adapt or fracture, whether uncertainty leads to reflection or reaction. This leads naturally to a more uncomfortable question. Control of information has always been central to governance. Throughout history, authorities have restricted communication during perceived crises. Printing presses were regulated. Newspapers were censored during wartime. In modern times, some governments filter internet access to limit organization or dissent. We now live in an era where information travels globally at near light speed. Communication infrastructure underpins finance, logistics, healthcare, and daily social life. This raises a question that sounds extreme until examined carefully. If a situation involving 3I Atlas generated genuine concern at the highest levels, would authorities attempt to restrict communication to manage the response? And do they have the capability to do so? The concept, often referred to as an internet kill switch, does not imply a single button. It describes the theoretical ability to partially or fully restrict access to communication networks during emergencies. In some countries, legal frameworks explicitly allow this. In others, executive powers could be interpreted to permit restrictions under national security justifications. The technical implementation varies. Network infrastructure contains choke points where traffic can be monitored, filtered, or blocked. Control over these points provides leverage over information flow. Real-world precedents exist. Several governments have implemented internet shutdowns during periods of unrest, elections, or security concerns. Egypt shut down much of its internet access during the 2011 revolution by ordering major service providers to disconnect international links. Myanmar has repeatedly restricted access in certain regions during conflicts. India has implemented localized shutdowns more frequently than any other democracy, blocking access in specific areas during periods of tension. These were not theoretical exercises. They demonstrate that the capability exists and that some governments are willing to use it despite economic and social costs. Could a similar action occur in response to 3I Atlas? For that to happen, several conditions would need to align. There would need to be genuine uncertainty or concern at governmental levels about the nature of the object. Authorities would need to believe that public knowledge of that uncertainty would cause more harm than good in the short term. There would need to be confidence that communication restrictions would not escalate the situation. International coordination would also be required. A unilateral shutdown by one country would not prevent information from spreading globally unless other nations cooperated or at least did not actively circumvent restrictions. Technical feasibility varies by political system. In centralized states with government control over providers, shutdowns are relatively straightforward. In decentralized democracies with private infrastructure, the process is more complex and legally contentious. Satellite-based internet presents additional challenges because it does not rely entirely on ground infrastructure. It is harder to control. Governments could attempt to jam signals or regulate ground stations, but these measures carry their own risks and limitations. Motivation matters more than capability. The concern would not be physical danger. The object poses no impact risk. The concern would be social disruption caused by rapid dissemination of paradigm-shifting information. If observations clearly contradicted natural explanations, public reaction, amplified through social media, could create what planners call an information emergency. In such a scenario, markets might react sharply. Social platforms could amplify extreme interpretations. Local authorities could be overwhelmed with questions they cannot answer. Religious and ideological groups might issue conflicting interpretations. Fringe movements could see validation and act in destabilizing ways. All of this could occur before institutions have time to coordinate messaging or provide context. From that perspective, temporary communication restrictions might be framed as a way to buy time, to slow information flow while understanding catches up. The counterarguments are substantial. Communication shutdowns in open societies are difficult to justify and hard to execute without backlash. The economic cost would be immense. Modern economies depend on constant connectivity. Interruptions would cause immediate losses and long-term damage to trust. Political costs would be equally severe. Citizens expect access to information, especially during uncertainty. Being cut off would likely deepen suspicion rather than reduce it. Practical effectiveness is also questionable. People would find alternative channels. Information would leak. Complete containment is unrealistic. A softer approach is more plausible. Selective throttling. Reduced bandwidth for non-essential services. Prioritization of official information sources. This approach is less visible, generates less resistance, and has precedent in emergency network management. For 3I Atlas specifically, the probability of any form of communication restriction remains extremely low. The object does not pose physical danger. The uncertainties, while interesting, are unlikely to justify such measures. The coordination required would be immense. Still, the fact that this discussion is possible matters. It reflects how seriously authorities consider information control during perceived crises. It highlights the central role of communication in modern stability, and it underscores that in an age of global connectivity, managing information can become as critical as managing physical threats. Practical preparation for maintaining communication during any potential disruption does not require extreme measures. It relies on redundancy and awareness. Having more than one way to contact the people who matter to you reduces dependence on a single system. Phone calls, text messages, email, social media platforms, radio broadcasts, and agreed physical meeting points each serve as backups if one channel fails. Keeping devices charged and maintaining access to portable power sources extends communication capability when infrastructure is strained. Equally important is the ability to access information without continuous connectivity. Downloaded maps, saved documents, and knowledge of local radio stations that continue broadcasting during outages provide continuity. These practices are not responses to cosmic events. They apply to storms, earthquakes, power failures, and other disruptions that already occur. They reflect the reality that communication systems, despite appearing permanent, depend on layered technologies that can fail. Preparedness in this sense has nothing to do with paranoia. It is a form of resilience. In a world where information shapes decision-making, maintaining the ability to communicate during uncertainty is a basic skill. It does not assume catastrophe. It acknowledges complexity. From this grounded perspective, attention shifts to a more uncomfortable possibility, one that scientists approach cautiously and the public finds difficult to ignore. What if 3I Atlas is not simply a comet? What if the unusual composition, the carbon dioxide-dominated activity, and the small deviations in trajectory are not accidents of nature, but features of design? This idea is not science. It is speculation, but it is informed speculation, rooted in the gaps between observation and prediction. The reason this idea arises at all begins with origin. 3I Atlas comes from outside the solar system. Its hyperbolic trajectory confirms that it is not gravitationally bound to the Sun. It entered once and will leave, carrying excess velocity that rules out a native origin. Whatever it is, it formed elsewhere. Its composition reinforces that sense of difference. A coma dominated by carbon dioxide rather than water suggests formation under conditions unlike those typical of solar system comets. The presence of an irradiated organic rich crust implies long exposure to galactic cosmic rays. The non-gravitational acceleration observed is explainable through outgassing. Yet it sits near the edge of model predictions, leaving a narrow statistical margin where alternative explanations are not strictly excluded. If one were to imagine designing a probe capable of surviving interstellar travel, it would likely not resemble popular images of metallic spacecraft. Interstellar space is unforgiving. High-energy radiation, micrometeorite impacts, and extreme temperature variations degrade exposed materials over long timescales. A more robust design might rely on natural materials. Ice provides radiation shielding. Rock provides structural stability. Sensitive components could be buried deep within, protected by kilometers of mass. Such a probe would likely remain inactive during the long transit between stars. Energy conservation would be critical. Activation could be triggered by environmental cues associated with arrival in a star system. Increased radiation levels, rising temperatures, or changes in surrounding plasma. These triggers would require no external command. This design philosophy would produce an object that looks natural: outgassing, coma formation. And apparently, cometary behavior would not be failures of disguise. They would be part of it. The object would not announce itself. It would blend in, minimizing the chance of interference by emerging civilizations. Within this framework, non-gravitational acceleration could serve a dual purpose. Most of it would be natural outgassing. A small component could represent subtle trajectory adjustments, not dramatic maneuvers, but minor corrections to ensure passage through regions of interest at optimal distances. Different probe archetypes have been proposed in speculative literature. A reconnaissance probe would be largely passive. Sensors would record data about stellar systems encountered. Communication might be delayed or highly directional, making detection unlikely. The probe would not need to interact. Observation alone would suffice. A more complex concept is the self-replicating probe, sometimes associated with the ideas of John von Neumann. Such a system would deploy smaller units as it encounters resources, creating a distributed network of observers. No such satellites have been detected around 3I Atlas. However, absence of detection does not imply absence of existence, especially if such components are small, inactive, or intentionally difficult to detect. Another possibility places 3I Atlas not as an active probe, but as a relic. Debris from ancient exploration efforts by civilizations that may no longer exist over billions of years. Countless such objects could wander the galaxy. Occasionally, one might pass through a system with emerging intelligence. In this scenario, the encounter is not intentional, it is incidental. If 3I Atlas were artificial, what signatures would be expected? Structured emissions would be the most direct indicator. Radio signals or optical patterns that differ from thermal radiation or reflected sunlight. Regular pulses, modulation, or frequency shifts that convey information. None have been detected so far. Trajectory adjustments inconsistent with sublimation models would also be notable. Energy expenditure beyond what outgassing could provide would demand explanation. Companion objects or fragments deployed in a controlled manner would suggest intent rather than natural breakup. Against these ideas stand strong counterarguments. Comets are common. Interstellar space likely contains vast numbers of rogue objects ejected during planetary formation. As detection capabilities improve, encountering such objects becomes more likely. Each unusual feature of 3I Atlas has a plausible natural explanation. Carbon dioxide activity, organic, rich crust, and slight trajectory deviations all fit within extended cometary physics. The philosophical complication arises from design expectations. An advanced intelligence would not necessarily build obvious machines. It might deliberately design probes to be indistinguishable from natural objects. This creates an observational bias. The probes most likely to be noticed are those least likely to exist. The concept of quiet observation applies here. If the goal is to study a civilization, announcing presence would alter behavior. A passive, patient probe would gather information without interference. It would record radio emissions, satellite activity, and atmospheric signatures. It might transmit its findings in a narrow beam unlikely to intersect with Earth-based receivers. If that were the case, 3I Atlas could be collecting data now while remaining observationally inert, assessing technological maturity, communication patterns, and planetary conditions. If so, the conclusions would likely be unflattering. A civilization capable of detecting interstellar visitors, but not yet capable of reaching them. Technologically advanced, yet fragmented, curious, but constrained. This scenario remains speculative. There is no evidence that 3I Atlas is artificial. Natural explanations remain far more likely. Yet the fact that such a hypothesis can be articulated without immediate dismissal is meaningful. It reflects the limits of current understanding. It reflects a universe that continues to challenge assumptions. Every interstellar visitor carries that potential. Whether it is ice and dust or something more, it forces a reconsideration of scale, origin, and possibility. Humanity's relationship with the cosmos is still evolving. This brings attention to another domain of uncertainty: physics itself. The laws that describe gravity and space-time are assumed to be well understood at the scales relevant to planetary motion. General relativity has passed every test to date, yet it is incomplete. It does not reconcile with quantum mechanics. At extreme scales, new behavior may emerge. Recent theoretical work in quantum gravity suggests that space-time may not be smooth. It may have structure at scales far smaller than current experiments can resolve. If gravity behaves differently under certain conditions, objects that have traveled through interstellar space for millions of years might experience effects not accounted for in existing models. It is important to be clear. As of now, no widely verified quantum gravity shockwave result has been confirmed. What follows is speculative, based on theoretical proposals and preliminary interpretations of gravitational wave data that some researchers claim hint at deviations from classical predictions. This is not established science. Gravitational wave observatories such as the Laser Interferometer Gravitational Wave Observatory, Virgo, and CAGRA have been detecting mergers of black holes and neutron stars for years. These detections have opened a new window on the universe. Some speculative analyses suggest subtle anomalies in the data that could point to deeper structure in space-time itself. At this point, the discussion reaches the edge of current knowledge. It illustrates how much remains unknown, and why interstellar objects like 3I Atlas draw attention from so many directions at once. Those gravitational wave detections match what general relativity predicts. Massive objects warp space-time, and changes in those warps move outward as waves traveling at the speed of light. The overall story is solid. The signal shapes are consistent. The timing is consistent. The physics works. But within that success, some theorists claim to see something extra. They focus on faint structure in the data, patterns that do not look like obvious instrument artifacts or known environmental interference. They argue that the residual noise may contain information, not about the source of the waves, but about space-time itself. The idea they point to is the possibility that space-time is not perfectly smooth at the smallest scales, at what is called the Planck scale, around 10 to the minus 35 meters. Some quantum gravity proposals suggest space-time could be granular, foamy, or fluctuating. In that picture, the smooth fabric described by Einstein is an average description, like how a solid table looks continuous even though it is made of atoms. If space-time has microscopic structure, the argument goes, gravitational waves traveling across the universe might pick up tiny distortions as they pass through that structure over immense distances. Those tiny effects might leave a faint signature in the data. For everyday life, this would likely mean nothing. At human scales, any graininess would average out. The distances we move through and the times we experience are so large compared to that tiny scale that the effect would wash away. Even for most objects in space, the same logic applies. Planets, asteroids, and typical comets move through space-time in a way that is well described by classical gravity. Any quantum texture would be far below what we can measure. But interstellar objects raise a question about accumulation. If something travels for extremely long durations across very large distances, could tiny effects add up, not in a dramatic way, not as a sudden force that changes direction? The suggestion is subtler, over millions or billions of years. Perhaps a small bias could emerge in how stress builds inside materials, how cracks propagate, or how volatile compounds remain trapped. Maybe the effect on any one moment is essentially zero, but the integrated effect is not exactly zero. This is where 3I Atlas enters the conversation again. It has been traveling through interstellar space for an unknown duration. Estimates based on its path suggest it could have been in transit for millions of years, possibly longer, depending on where it formed and how it was ejected. During that time, it was exposed to cosmic radiation and micrometeorite impacts, both of which we understand in broad terms, but it was also traveling through whatever space-time truly is at the smallest scales, whether smooth, granular, or something else we have not yet described correctly. If quantum gravity effects exist, then an object that has spent so long in deep space might carry subtle traces of that exposure, not as a clear label, and not as a direct measurement, but as small residuals in behavior. Perhaps in how its structure responds to heating, perhaps in how it retains gases in deep cold, perhaps in tiny aspects of its motion that remain after we account for gravity, outgassing, and rotation. This connects in an interesting way to cosmic ray processing. We already have a well-established story for how high-energy particles alter the surfaces of icy bodies. Cosmic rays break chemical bonds. They transform simple ices into more complex molecules. Over long times, they can build an irradiated crust rich in organic compounds. That process is often modeled under the assumption that space-time is effectively smooth for the chemistry involved. But cosmic rays themselves do not travel in isolation. They move through electromagnetic fields, and they are influenced by the gravitational environment they cross. If space-time has quantum structure, then in principle, the propagation of cosmic rays could also be affected in tiny ways. That does not mean cosmic ray chemistry would suddenly behave differently in an obvious way. It suggests a more modest possibility. Perhaps a small fraction of the chemistry in an interstellar crust could reflect interaction pathways that do not match our simplest expectations. The result would not be impossible molecules. It would be chemistry that looks almost familiar, but not perfectly aligned with a basic radiation processing model. In a remote sensing context, that kind of subtle mismatch could show up as weak spectral features, unusual ratios, or results that require extra assumptions to explain. This remains extremely speculative. There is no widely verified evidence that space-time is granular at the Planck scale. There is no confirmed quantum gravity signature in gravitational wave data that the broader physics community accepts as established. And there is certainly no proof that such effects would meaningfully influence interstellar comet behavior. The point is not to claim that 3I Atlas is showing quantum gravity. The point is to recognize how much fundamental physics remains unsettled, and how those open questions apply to everything we observe, including rare visitors from other star systems. It also helps frame what would count as meaningful anomaly. If future observations of 3I Atlas revealed behavior that resisted explanation after we accounted for composition, rotation, non-gravitational acceleration, and measurement errors, that would force a choice. One possibility would be simple: our comet models were incomplete. Another possibility would be that our measurements were wrong. But there is a third possibility, less likely but important to keep in mind. The anomaly could point to physics beyond what we currently include in standard models. Effects that only become visible after long exposure to deep space conditions that solar system objects rarely experience. In that sense, 3I Atlas is not only an object of interest, it functions as a scientific probe. Not in the sense of an engineered craft, but in the sense of a natural experiment delivered to us. We cannot run a million-year spacecraft mission and watch how materials change under interstellar conditions. Nature has already done that. Interstellar objects are the return samples of that experiment. And our job is to learn what we can from their light, their motion, and their chemistry. That is why December 19th is not simply a date for watching an object pass. It is a moment that highlights the limits of our knowledge. It reminds us that the universe contains processes we have barely begun to test. Whether quantum gravity is real, whether it affects 3I Atlas, those questions remain open, but the mindset of being careful with conclusions, curious about gaps, and willing to revise models is the right approach to anything that arrives from beyond our solar system. History shows that confidence in a complete understanding is often premature. While 3I Atlas draws attention because it is physically present in our own sky, other discoveries from this year point in the same direction, toward a cosmos that is more chemically active and more interconnected than earlier generations imagined. The James Webb Space Telescope, when it is not observing comets or interstellar visitors, has been reshaping how we understand exoplanets, worlds orbiting other stars. These planets matter because they give us the best chance to study environments where chemistry could support life, even when we cannot visit them. In 2025, one particular atmospheric detection has attracted attention because of what it suggests about organic chemistry and volatile-rich worlds. The object involved is commonly described as a super-Earth or a sub-Neptune-type planet orbiting in the habitable zone of a red dwarf star roughly 40 light-years away. The exact details of the system may evolve as analysis continues and peer review progresses. But the basic observational method and the core findings are stable enough to discuss as a category of result. The method is called transit spectroscopy. When a planet passes in front of its star, a small portion of the starlight filters through the planet's atmosphere before reaching the telescope. Webb can split that filtered light into its component wavelengths, like separating white light into a rainbow. Different molecules absorb specific wavelengths, leaving patterns in the spectrum. Those patterns allow scientists to infer which gases are present. In this case, the spectrum shows water vapor, which is expected in many atmospheres. It shows carbon dioxide, also expected, but it also shows methane and more complex hydrocarbons in ratios that do not fit simple chemical equilibrium models. One ratio in particular has received attention: the methane to ethane ratio. In a purely abiotic atmosphere, shaped only by sunlight-driven chemistry and basic thermodynamics, certain proportions are expected given the star's radiation, the planet's temperature, and the available elements. The measured ratio is not wildly off. It is not a dramatic signature that forces only one conclusion, but it is measurably shifted in a direction that could suggest unusual chemistry or a source process that is not captured by the simplest models. No one is claiming a definitive biosignature from this data alone. The most responsible interpretation is that multiple explanations remain plausible. Follow-up observations are being planned to look for additional molecules that could reduce ambiguity. Some molecules, if found together in certain patterns, could strengthen a biological interpretation. Others could favor geology, photochemistry, or atmospheric dynamics. The key point is that the data is interesting because it pushes beyond a clean % day. Simple story. This connects back to 3I Atlas in more than one way. First, if exoplanets can host atmospheres rich in complex organic molecules, then the planetary systems they belong to likely also produce organic-rich comets and asteroids. In planetary formation, volatile material accumulates in the outer regions of young systems. Over time, that material can form icy bodies. Gravitational interactions can eject some of those bodies into interstellar space. That process can produce rogue comets that later wander into other star systems, becoming objects like 3I Atlas. In that view, the organic chemistry hinted at in an exoplanet atmosphere and the organic-rich crust inferred on an interstellar comet are different expressions of the same basic fact. Complex molecules can form naturally in many environments. They are not rare. They are not unique. They are part of what carbon chemistry does when energy and time are available. Second, these findings reinforce that organic chemistry does not require life. The elements involved, carbon, hydrogen, oxygen, and nitrogen, are abundant across the universe under the right conditions. Chemistry builds complexity. 3I Atlas represents one pathway where cosmic rays and long exposure transform ices into complex organics. Exoplanet atmospheres represent another pathway where starlight drives photochemistry in gases and clouds. Different environments, different mechanisms. Similar conclusion, complexity can emerge without biology. Third, and more speculatively, both lines of evidence support the idea that star systems may not be isolated in their chemistry. If comets and asteroids are routinely scattered into interstellar space, then material exchange between systems is possible. It would not be fast. It would not be common on human timescales. But over billions of years, a slow exchange could connect systems. In that picture, the galaxy is threaded with wandering objects carrying chemical histories from one place to another. 3I Atlas could be one example. A natural sample return from its origin system. Delivered by gravity and time, a shared challenge sits under both the interstellar comet story and the exoplanet atmosphere story. Most of what we know in modern space science comes from remote sensing. We analyze light from objects we cannot physically touch. We infer composition from spectral patterns. We infer structure from brightness changes. We infer motion from tracking data. Our conclusions depend on instrument sensitivity, on calibration, and on the models used to interpret signals. Sometimes the data yields clear answers. Often it does not. Often it provides a range of possibilities that fit within error bars. Each possibility requires different assumptions. For 3I Atlas, we detect organic molecules and infer that they formed through radiation chemistry. That is the simplest explanation. Yet it is not the only imaginable one. If shielded pockets exist deep inside the nucleus, some chemistry could be preserved from the origin system in ways that are difficult to detect remotely. We cannot completely rule that out. For the exoplanet atmosphere, we detect hydrocarbon ratios that do not match simple equilibrium models and consider whether biology could play a role. But there are also non-biological explanations. Stellar activity could drive unusual photochemistry. Geological processes could release gases in ways that shift ratios. Atmospheric circulation could redistribute compounds unevenly. From 40 light-years away, we cannot confirm life based on ambiguous spectral features. This is why humility matters. Not as philosophy, but as method. Cosmic observations rarely provide absolute certainty. They provide constraints. They narrow the field of plausible explanations. They guide where to look next. The universe is chemically diverse. Conditions vary widely. Outcomes vary widely. And our ability to interpret from a distance is limited by what photons can carry and what models can capture. At the same time, the most important development is that these questions are now being asked with real data. We are detecting organic molecules in exoplanet atmospheres. We are characterizing interstellar visitors. We are building instruments capable of measuring cosmic chemistry in ways that were impossible a generation ago. Ambiguity in current results does not mean failure. It means the frontier has moved. Easy questions have been answered. What remains is genuinely hard. And it will take better instruments, more observations, and deeper theory to reduce the uncertainty without turning it into overconfidence. 3I Atlas and that exoplanet roughly 40 light-years away are linked by the same basic cosmic processes. The same physics governs how matter moves. The same chemistry builds molecules when the right elements and energy are present. The environments are different, but the rules are the same. Studying one helps us interpret the other because both are snapshots of how the universe builds complexity under different conditions. Taken together, they also point to a larger lesson. The galaxy is not a set of perfectly sealed star systems. Over long timescales, material can leave one system and enter another. It happens slowly, and it may be rare on a human calendar. But over millions and billions of years, it becomes meaningful. Bits of ice, rock, dust, and chemistry can wander between stars. That raises a quiet possibility that every system may carry traces, however small, of countless other systems, mixed and blended through encounters we are only now learning to detect. While attention is focused on whether intelligence might arrive from the sky on an interstellar visitor, a different kind of intelligence has been raising difficult questions much closer to home. In late 2025, a major artificial intelligence research lab announced that one of its systems completed a complex scientific task with minimal human intervention. The system did not only help with a single step, it designed an experiment, analyzed results, formed hypotheses, and proposed follow-up tests in a loop that resembled human scientific work, but ran at machine speed and scale. The announcement triggered immediate controversy. Supporters saw progress toward autonomous scientific systems that could accelerate discovery. Critics warned about unpredictability, weak oversight, and the risks of trusting systems whose internal decision-making is hard to interpret. The achievement was significant, but it did not appear out of nowhere. Artificial intelligence has assisted science for years, finding patterns in large datasets, improving image analysis, helping propose molecular structures, and supporting drug discovery. What changed in 2025 was autonomy. Earlier systems usually required people to define the problem, choose methods, judge results, and decide what to do next. This newer system acted more independently. It pursued goals using strategies it developed rather than following a narrowly scripted path. That shift matters because it moves the system from being a tool that extends human capability to an agent that can choose actions within a goal framework. This connects back to 3I Atlas in a practical way. If people seriously consider whether an interstellar object might be an artificial probe, they need to consider what artificial intelligence might look like in real life, not in fiction. Stories often train people to expect conscious machines with emotions and motives similar to humans. But the artificial intelligence being built today is different. It is an optimization system. It is pattern recognition. It is goal-directed behavior that does not require feelings, self-awareness, or anything like a human mind. A probe built by another civilization might be similar in that sense. It might not be aware in a way we recognize. It could be a system designed to gather data, make choices, and adjust to circumstances without inner experience. If so, looking for intelligence becomes less about listening for friendly messages and more about identifying behavior that suggests purpose, not a greeting, but evidence of goal-directed activity, structured response, or patterns inconsistent with natural processes. The same qualities that make a highly autonomous artificial intelligence interesting to study on Earth would be useful in a long-range probe. A probe sent on a journey lasting millions of years would not be piloted by a biological being. A conscious traveler would face impossible problems of time, resources, and survival. A more realistic approach would be an optimized decision system embedded in protected hardware. It could remain dormant during the long cruise phase. It could activate when it encounters a new star system, collect data, and make decisions based on programming set long ago, perhaps by creators who no longer exist. That framing also highlights a shared set of concerns. When autonomy increases, questions of trust and safety rise. Can we trust systems we do not fully understand? How do we manage agents whose decision pathways are opaque to outsiders? What safeguards prevent unintended consequences when a goal-driven system finds unexpected ways to pursue its objectives? These questions apply whether the system is a neural network trained on Earth data or a hypothetical probe optimized for interstellar reconnaissance. In both cases, the intelligence is not biological cognition. It is architecture, rules, and behavior that can be consistent within its own framework while still feeling alien to us. The issue of containment becomes especially relevant with autonomy. On Earth, we can implement safeguards. We can test systems in controlled settings. We can monitor outputs. We can shut systems down if they behave outside allowed boundaries. But none of those options apply to an interstellar visitor already passing through the solar system. We cannot contain it. We cannot stop it. We cannot reach out and flip a switch. We can observe, model, and interpret. But control is not a realistic option at current technological levels. That leads to an uncomfortable realization. Humanity struggles with governance, interpretability, trust, and safety around artificial intelligence are not separate from the question of alien artifacts. They are a preview. If we ever encounter technology from elsewhere, the hard part may not be proof that it is artificial. The hard part may be understanding its purpose and behavior from the outside. If 3I Atlas were artificial, it would almost certainly be optimized for a specific mission. That mission might be data gathering during flybys, survival in deep space, and perhaps communication or replication. Inferring that mission from remote observation would be like trying to reverse engineer an advanced artificial intelligence by watching what it does, without access to its training data or internal design. You can measure behavior. You can infer constraints. But certainty is hard. There is also a possibility that reduces fear rather than increasing it. An autonomous scientific system on Earth is not trying to dominate or destroy. It is trying to understand within the goals set for it. A probe, if it existed, might be similar. Observe, record, and possibly transmit. It would not need to be hostile. In many scenarios, it would be indifferent. Its objectives might not include humanity at all. The largest risk could come from misunderstanding and reaction rather than from the object's intent. This reframing makes potential alien technology both less and more alien. Less alien because humans are already building non-human intelligence and learning its limits. More alien because machine intelligence is fundamentally different from biological thought. Even our own systems can be described mathematically, yet understood only indirectly through behavior. We cannot know what it is like to be an artificial intelligence. And we would face the same limit with any probe from another star. We could only observe and infer. As 3I Atlas recedes after December 19th, the parallel remains. Humanity is creating intelligence that is not human. If intelligence exists elsewhere, it may also be non-human in a deeper sense. Possibly artificial, optimized for tasks rather than experience, over long timescales. The line between natural and artificial, between biology and technology, may matter less than the ability to recognize intelligence in varied forms and respond wisely. This leads to another reminder about uncertainty. Closer to home, inside our own solar system. The solar system feels mapped and familiar. Planets have been charted, thousands of asteroids are cataloged, comets are tracked. Spacecraft have visited every major world and many minor bodies. It would be reasonable to assume few big surprises remain. Yet in late 2025, new statistical analyses of distant outer solar system objects have continued to suggest that something large and unseen may be shaping orbits far beyond Neptune, the idea commonly called Planet 9. Or possibly something stranger. Remains one of the most compelling open mysteries in modern astronomy. The evidence is indirect. It comes from the orbits of extreme trans-Neptunian objects. Small bodies with paths that keep them far from Neptune for most of their long revolutions. Some of these objects show a kind of clustering. Their orbital orientations appear aligned more than random scattering would predict. The simplest explanation is that a massive body is shepherding them, nudging their orbits through gravity over long periods. Statistical work has suggested that the chance of such alignments appearing randomly is less than 1%, pointing toward a real dynamical cause rather than pure coincidence. That sounds persuasive. But it is not the end of the story. Statistics in astronomy are always entangled with what we can and cannot observe. Observational bias is a serious alternative explanation. If surveys are more likely to find objects in certain parts of the sky, at certain brightness levels, and at certain orbital angles, then the sample may look clustered even if the full population is not. Researchers have proposed a range of explanations. One is a planet with a mass roughly 5 to 10 times that of Earth, orbiting at several hundred astronomical units from the Sun. At that distance, it would be faint, slow-moving, and easy to miss with existing surveys, yet massive enough to shape the outer solar system over time. Another explanation is that there is no single planet at all. Instead, many smaller bodies could collectively create a gravitational effect, like a distant disk of material that has not been fully characterized. A few proposals go further. Some suggest a primordial black hole captured by the Sun's gravity. Others suggest subtle modifications to gravity at extreme distances, where the solar system's edge becomes a natural test region for dynamics. Another idea is that an interstellar object could have been captured billions of years ago and left in a long period orbit, becoming an unseen sculptor in the dark. The connection to 3I Atlas is not direct in the sense of shared origin or shared path. It is thematic. If our own solar system can still hide a massive object, then the inventory of what exists in our cosmic neighborhood is not complete. Assumptions about how well we understand the solar system may need recalibration, especially at the edges where gravity is weak and orbital periods stretch into extremely long timescales. That also reframes how unusual interstellar visitors may be. Perhaps interstellar capture occurs more often than models predict. Perhaps the outer solar system contains a population of captured rogue planets or large comets that entered the Sun's sphere of influence early in its history and were stabilized into distant orbits. Perhaps the story of solar system formation and evolution is incomplete in ways that only become obvious when we study the most distant objects. The search for Planet 9 is intensifying as survey capabilities improve. New strategies focus on regions of sky that were historically underobserved. The Vera Rubin Observatory, expected to begin full operation soon, is designed to image large portions of the visible sky repeatedly, creating a detailed database of moving objects. That kind of repeated, wide-field monitoring should help confirm or rule out the existence of a distant massive body within a few years. Until then, the field remains in a state of tension between hint and proof. Statistical anomalies suggest something may be there, but definitive detection has not arrived. That uncertainty about our own solar system amplifies the broader theme running through 3I Atlas. Exoplanet chemistry. An autonomous artificial intelligence. Confidence should be calibrated to evidence. If it is possible to miss a body many times the mass of Earth in our own cosmic backyard, then it is also possible that we are missing many smaller things. Interstellar objects could pass through undetected because they are faint, because they move through regions we are not watching closely, or because our surveys are still improving. The sky can look well known while still holding gaps. And those gaps matter most when a rare visitor briefly makes them visible. How often does material from other stellar systems enter ours? And how much of what we classify as solar system natives might actually be captured interstellar visitors that arrived so long ago we can no longer tell the difference? Those are not questions with clean, final answers yet. But the underlying physics is clear enough to frame what is possible. Capture is complicated in detail, but simple in principle. A true interstellar object enters on a path that is not bound to the sun, meaning it has more than enough energy to pass through once and leave. To become captured, it must lose some of that energy during its passage. If it loses enough, the orbit can shift from an open, one-time path to a bound orbit that keeps it in the solar system for a long time. There are several ways this can happen. A gravitational assist is the most straightforward. If the object passes near a planet at the right geometry, the planet can exchange a small amount of orbital energy with it. Most flybys do not result in capture, because the alignment has to be extremely specific, but the mechanism exists. And over very long spans of time, rare alignments still occur. Another possibility involves drag, not in the everyday sense of air resistance, but in weaker forms of interaction with the environment of the solar system. The solar wind and the interplanetary medium are thin, but they are not zero. For most objects, the effect is negligible, yet in special cases, for small fragments or for extremely long durations, weak forces can matter in ways that are easy to dismiss at first glance. Close encounters can also lead to fragmentation. If an object breaks apart, some pieces might lose more energy than others. One fragment may escape while another remains bound. This does not require intention or unusual physics. It requires only the right encounter conditions and an object fragile enough to split. All of these processes are rare, but the relevant timescale is not a human lifetime. It is billions of years, given enough time, and given the likelihood that interstellar objects pass through planetary systems more often than older models assumed. The chance of some capture events becomes meaningful. The early history of the Sun adds another layer. The Sun likely formed within a denser stellar cluster than the environment it occupies today. In a crowded stellar neighborhood, close encounters between stars and their debris fields would have been more common. That means exchange of material, including capture, would have been more likely in the early solar system than it is now. Under those conditions, some captures almost certainly occurred. If that is true, then the outer solar system could contain dozens, or even hundreds, of objects that originated elsewhere and were captured long ago. They would be difficult to detect because they are small, distant, and faint. Many would spend most of their time far beyond the regions where surveys have historically been strongest. Even if discovered, They might look like typical distant bodies unless we could measure their chemistry in detail. Seen in that context, 3I Atlas becomes less of an exception and more of a visible example of a broader process. We noticed it because it passed close enough, and because it became active and brightened as it approached the Sun. But for every interstellar visitor detected, how many pass through the outer solar system undetected? Too faint to trigger instruments or moving through parts of the sky that are not being monitored intensively. And among those that pass, how many were captured long ago and now orbit quietly in the far outer reaches? They could be indistinguishable from other distant objects unless we can measure composition precisely enough to see chemical or isotopic ratios that do not match standard solar system formation expectations. That kind of measurement is extremely challenging at great distances, and it is one reason these questions remain open. The larger implication is that solar systems are not sealed environments. They are regions where a star's gravity dominates locally, but does not create a perfect barrier against exchange with the galaxy. Material can enter by direct passage, as 3I Atlas did. Material can enter by capture into long-term orbits. Material can also leave. Planetary interactions can eject comets and asteroids into interstellar space, where they may wander until they encounter another star system and repeat the process on a galactic timescale. Over millions and billions of years, this slow exchange could amount to a kind of cosmic mixing, not a rapid blending, and not an equal distribution, but a persistent trickle of matter and chemistry that links systems that appear isolated on human timescales. This is why the search for Planet 9 and the study of 3I Atlas belong in the same conceptual frame. One is about a possible unseen mass shaping distant orbits. The other is about a confirmed visitor from beyond the solar system. Both push against the idea that our solar system is fully inventoried and fully understood. Both suggest that the boundary between what belongs to the solar system and what does not is fuzzier than a simple bound versus unbound label implies. They also reinforce a basic point about time. The universe changes on timescales that are long compared to human observation. But those changes still leave traces if we observe carefully enough, and if we remain flexible about interpretation. We can detect evidence of processes we cannot watch unfold in real time. As December 19th approaches and 3I Atlas completes its passage, it is worth remembering that other objects may be waiting beyond Neptune, some native and some not. Together, they participate in the gravitational dynamics that decide which comets visit the inner solar system and which remain forever in the cold outskirts. The sky is not empty. The solar system is not static. Every object we detect, whether clearly interstellar like 3I Atlas or faint and ambiguous like the hypothesized Planet 9, adds a piece to the picture of how matter moves through space and time. That shift in perspective sets up the final scale change. If we want to understand what one interstellar comet might mean, it helps to zoom out to the largest context we have, not because dark energy explains comets, but because the same lesson appears at every scale. The universe contains phenomena we do not fully understand, and our models become less certain at the extremes. This is where dark energy enters the discussion. Dark energy is the name given to whatever is driving the accelerated expansion of the universe. It was inferred in the late 1990s, when observations of distant supernovae indicated that cosmic expansion is speeding up rather than slowing down, as gravity alone would predict. In current cosmological accounting, roughly 68% of the universe's energy density is associated with dark energy, a component that behaves as if it pushes space apart. The standard cosmological model often treats dark energy as a cosmological constant, meaning it is uniform and unchanging through space and time. In that framework, it is a property of the vacuum itself. This approach fits a wide range of observations. But there is ongoing work exploring whether dark energy is truly constant or whether it could vary slightly across space or change slowly over time. Even a small variation could have large implications for cosmology. Some recent theoretical papers, not broadly confirmed and not treated as settled by mainstream cosmology, have discussed subtle anomalies in the cosmic microwave background. The cosmic microwave background, often shortened to the CMB, is the afterglow of the early universe. It is made of photons that have been traveling through space for more than 13 billion years, gradually cooling as the universe expands. Measuring its temperature across the sky allows cosmologists to map tiny fluctuations in the early universe and test models of cosmic evolution. The CMB temperature is extremely uniform. The small variations that do exist are on the order of parts per million. That near uniformity is one of the strongest pillars of modern cosmology. It tells us that the early universe was remarkably smooth, with tiny ripples that later grew into galaxies and large-scale structure. The speculative claim in these papers is not that the CMB is wildly uneven. It is that one region might show a slightly larger temperature depression than standard models predict. The interpretation offered is that this could hint at an interaction between CMB photons and dark energy, or at least at physics not fully captured by the simplest assumptions. This remains preliminary. It is not a confirmed discovery. It is a hypothesis built on subtle signals and complex analysis. Why mention it in a discussion centered on 3I Atlas? Not because a comet has any direct connection to dark energy on billion light-year scales. It does not. The link is thematic, at every level, from the smallest scales of quantum proposals to the largest scales of cosmic expansion. We encounter domains where current models are powerful but incomplete. 3I Atlas sits in that boundary region for planetary science. It is not that comet physics is unknown. We understand outgassing, coma formation, and non-gravitational forces well. In many contexts, the uncertainty comes from limited sample size and unfamiliar history. An interstellar visitor carries chemistry and structure shaped outside our solar system. It may still fit our models, but it also tests them in regimes we cannot easily reproduce. The dark energy temperature drop idea, if it were ever confirmed, would function similarly for cosmology. It would not erase the successes of current models. It would introduce a refinement, forcing cosmologists to reconsider assumptions about uniformity and constancy. The parallel is not about claiming equivalence. It is about method confidence should come from repeated testing, not from habit. If future observations of 3I Atlas or other interstellar visitors reveal persistent residuals that resist explanation even after we account for rotation, composition, and non-gravitational acceleration, we would face a choice. The most likely explanation might still be mundane measurement limits, incomplete modeling, or unaccounted physical processes within ordinary cometary behavior. But the possibility exists that unusual objects expose gaps in our frameworks. There is one additional point worth keeping in mind when thinking about interstellar travelers. The universe is expanding. Space itself is stretching. At the scale of the solar system, that expansion is negligible compared to local gravity and motion. It does not change how planets orbit or how comets move in any measurable way. But over interstellar distances and over immense timescales, expansion is part of the environment. An object like 3I Atlas has traveled through a universe that has been expanding for the entire duration of its journey. The space it crossed was not static in the largest sense. That does not mean expansion changes its trajectory in a way we can detect in a short observational window. It means that true interstellar travelers experience conditions and timescales that no solar system native object experiences in the same way. Interstellar objects are time capsules. They carry information about their origin systems. But they also carry information about the journey itself, about what deep space does to matter over durations longer than human civilization has existed. We model that journey with physics and chemistry. We infer its effects from surface processing, volatile loss, and radiation products. But we cannot observe the full process directly. We can only study the results when an object arrives. When we step back and look across the full set of uncertainties explored, a consistent pattern appears. There are uncertainties in light curves and trajectory refinements. There are uncertainties in electromagnetic interactions and in how organic chemistry forms and persists. There are uncertainties in how to interpret ambiguous data from remote sensing. Whether from interstellar comets or exoplanet atmospheres, there are uncertainties at the extremes of physics itself. From quantum-scale proposals to dark energy questions in cosmology, December 19th may pass quietly. It may become simply a date when a scientifically interesting interstellar comet reached closest approach and continued on its path. Or it may become a moment that pushes us to revisit assumptions. Not because of danger, but because of what a visitor from another system represents. The readiness protocol discussed throughout is not primarily about physical preparation. Basic communication resilience has value in many ordinary emergencies, and it remains sensible regardless of cosmic events. The deeper readiness is intellectual. It is the habit of accepting that the universe is under no obligation to match our expectations. It is the discipline of staying curious and critical at the same time. It is the willingness to follow evidence while demanding strong proof for extraordinary conclusions. Whether 3I Atlas is a comet, a probe, or something we lack the vocabulary to describe well, it represents an opportunity to learn about processes operating across timescales and environments outside direct human experience. The sky changes slowly by human standards. Yet cosmic discovery accelerates as instruments improve. A century ago, the existence of other galaxies was not fully accepted in the way it is now. A few decades ago, exoplanets were still largely unknown. More recently, interstellar visitors were not part of observational routine. Each step expanded what could be tested. 3I Atlas is one data point in that larger trajectory, a visitor reminding us that space is not empty, that stellar systems exchange material, and that chemistry can travel. Whether December 19th changes anything depends less on the object itself than on how we interpret it and what we learn from it. In that sense, the message is not a warning, it is information. Written in motion, in ice, in dust, and in chemistry. The challenge is understanding it carefully, without fear and without premature certainty.